Welcome to lecture 12 of the digital logic class, and the title of this lecture is Design of Sequential Circuit. So let's talk about in general what we need to do in terms of design of sequential circuit. As we indicated in the last lecture, okay, so design of sequential circuits, and what we need to do here basically, first of all, typically in the design of sequential circuit, we start with a description of the circuit, description of what the circuit does. Okay, typically either English description or I have a state diagram. If I don't have a state diagram, the very first step will be is to construct a state diagram. Okay, state diagram. And state diagram, basically, as we have seen before, it is a diagram where you have these nodes are the states and these arcs are the transitions between these states. Okay, all right. So this is the state diagram. From the state diagram, we construct the state table. And state table, by the way, if you have a state table, you should be able to get state diagram. If you have a state diagram, you should be able to. So they represent the same thing. So just to refresh your mind, okay. So a state table is typically in the state table, okay. You will have a present state um, and input, okay, and next state and output. Okay, so that's basically the uh, the state table. Okay, then from the state table, what we will do, we will try to have. Uh, now, of course, we will do some kind of assignment of binary code to the states. We assign uh, states um, binary code. Okay, and this what it says basically. If this is a state A, we will represent state A of 0 0, for example. All right, where 0 0 represents two flip-flops, Q1 and Q0. Okay, we will see this in the exercise, but we are just going through the process. Typically, if you are a good designer, you will merge these two steps in one step. Then we have to find the flip-flop input values. The flip-flop we found out, so we calculate the flip-flop input values. Okay, values. Okay, and this is basically in this table. What we will do is that we will add here. Uh, I'm sorry. We'll add here another column. So it's the same as the state table. So we have a present state. Okay, state. Okay, input. Next state, output, and flip-flop inputs. Flip-flop inputs, okay? And these are the flip-flop inputs. Flip-flop inputs, okay? So we will see how we'll do that, but this is the general process, and we have to find out the values, etc. Sometimes people put this output at the end, sometimes in the middle. It doesn't matter, but it's we add the flip-flop inputs to our state table here. And then we for those flip-flop inputs, we minimize them with K-map, okay? And then finally we draw the circuit. Okay, so remember, in analysis, what we did in analysis, we started with what? We started with the circuit, and we stopped with the state diagram. Now we are, so that was the process. Now we are exactly reversing this process. Okay, We are doing exactly because what we are doing here is design. Last lecture, what we did analysis. Okay, all right. So let's take an example here, and this example should illustrate what we want to do. Okay, so here's an example, and the example basically says we want to have a sequence detector. We want to implement a sequence detector. Okay, a sequence detector or a recognizer. So sequence detector or recognizer, detector or recognizer or recognizer. It's both are the same. And basically what happened, I have a system, I have a system where I have a wire, let's call it X, and there are bits that comes through this bits, bunch of bits, okay? And I need to detect in this circuit if I see a certain pattern on X. So for example, I want to see if I received 1001 on wire X. Remember, X is a wire that transmits 1 bit. And my system has an output Z which will go 1. Z will equal 1 if I see 1001. Okay, so we call this type of circuit a sequence detector. So basically, for example, let's assume, for example, X transmits the following bits. Let's say, for example, 1, 1, 1, 0, 0, 1, okay, 1, 1, 0, 0, 1, 0, 0, 1, 1, etc. Now the output Z will come in here and say, okay, so here's output Z. It says, okay, how about here? Well, we don't have history, so Z is 0. How about here? We just saw these 2 bits. They are not 1, 0, 0, so Z is 0. Well, how about here? We saw 1, 0, so they are not my sequence, so it's 0. Well, how about here now? Well, we have these bits here. They are not 1001, so 0. Okay, 0. Now how about here? Here we see that we have 1001. So I have the pattern here complete, the one that so Z now becomes 1. Okay, but how about now here? Well, here the last 4 bits pattern, from this bit is 0011, which is not 100 that the one I detect. So this is an output of a 0 here. How about here? It says 0. So we stay here until I come in to this bit here. So I have seen what? I have seen 1001. So Z is 1. And now watch here, 0, 0, and then here I have another 1. Now notice that here I have overlapping 10. So this is a pattern here of 1001 and it overlaps with the other. So this one here serves, this digit 1 serves as a purpose as an end of a pattern and a start of a pattern. Okay, so this is what we need to do. We need to design the circuit that gives me this output Z. Okay, so we need the very first thing. So now we understood the circuit. We need to construct what? The state diagram. Okay, we need to construct what? The state diagram. Okay, so let's construct the state diagram. All right. Well, it turned out I as X. So what's my input here? Well, in this circuit, my input is X, and my output is Z. Okay, so you will see me in the arcs now from a state to a state. I'm gonna make something like this slash this. This is will be X, this will be Z. Okay, so let's start with the following states. So let's make our state diagram. Okay, so we're gonna start with a state. We're gonna call it state A. Okay, all right, state A, and state A is the initial state. I want to move to another state. I'm going to call this state B if I receive a 1, which means x equals 1. Okay, oops, sorry. Okay, and the output stays 0. Now, what does the state B mean? State B means that I have seen 1. I have seen 1. So the very first, now, but remember that I need to detect 1, 0, 0, 1. I need to check. No. Now, so the next bit that I need, so I need to detect this sequence. I need to check. So now I remember that I have seen 1. So I need to detect that I have seen a 0. Then I go to another state when I receive a 0, again an output of a 0. So C here means that I have seen what? 1, then 0. I have seen 1, okay? I have seen 1, then 0. I have seen 1, then 0. Okay, now, so I need to check if I have received this. So I need another state. Let's call it D, okay? So D means what? Well, D means I will go to it if I have let's see here, one if I have a 0. Okay, okay. So now I will go to this state if I have, so which means I have seen 1, 0, 0. So state D means that I have seen 1, 0, 0. Okay, so I have seen 1, 0, 0. I'm left with what? I'm left with the last one. Okay, so now the last one, I'll take it and say, okay, so I'll take it to this state A, right? And at that moment, the output will be 1. The rest one will be what? Will be zeros. The output will be 0. Okay, now because I'm allowing overlapping, like in this case here, so the problem allows me to overlap this one, the last one that I have seen. So basically here I am in this arc when I have completed 1, 0, 0, 1. But this one could be a start of another sequence. So instead of going to A, I have to go to B. So when we say, okay, okay, so the right thing to do is really not to go to A, rather to go to B. So we have to go to B. Okay, so let's go back here and say, okay, A, we go to B here because this is could be the end of a sequence and at the same time the start of another sequence. So I have to go to B. So B now remembers that it has received a 1. Okay. Now remember, as we have learned from previous lecture, in the state diagram, I have to think of all the possibilities. So now let's think of the other possibilities for input A. From this state, state A, I have, excuse me, I have A, okay? I have A with an arc goes out when x equals 1. Well, what about when x equals 0? Well, when x equals 0, it means I did not start the sequence. So I stay in the initial state A. So I'm going to stay here when input is 0 and with the output 0. Okay, how about B here? So B, remember B, it is the state where I have seen a 1. But what happened, and then I'm going to leave to the next state if what? If I receive a 0, so that now I remember 1, 0. But what if B, I received, instead of a 0, I received a 1? In this case, I stay in B. And why stay in B? Because I might be getting this pattern 1, 1, 1, 1, 1, 0, 0, 1. So any one of them at the end could be the start of it. So it's better to stay in state B. All right. So state B basically are counting those ones. So and the hope that we are starting a new pattern. Okay. So we don't go to. So if I received a 1, I stay in B. but the output is 0. Well, how about when I am in C? Suppose, so C says that I have received what? 1, 0. So if I receive a 0, I go to state D. But what happened if I receive a 1? So if I receive a 1, it looks like I'm receiving 1, 0. So this one takes me to state B. This takes me to state C. So if I receive another one, where should I go? The best thing is to go to state B, hoping that you are starting a new series. So if I receive a 1, I go to a state B. I'm hoping that I'm starting the correct sequence. So this is a 1 and an output of a 0. Okay. Now let's go to state D. In state D, we know that we have received 1, 0, 0, and we are waiting for the 1 to output 1. But what happened if I received 1, 0, 0, and instead of a 1, I received a 0? Well, that breaks everything. I have to go back to the idle state. So now here, if I received a 0, okay, so I have to go all the way here to this state, okay, if I receive a 0, and it will be an output of a 0. Now, this is the complete state diagram of my circuit that I described. Notice every state goes from it two arrows. Why two arrows? Because I have one input, and this input can be a 0 or can be a 1. And for every arrow, I have an output. Notice that this type of circuit is a Mealy circuit, not more. It's a Mealy because the output is dependent of the input and the state. Okay, right now, so this is my state diagram. Now, what I need to do, let me just use the eraser here. Oops. What I need to do is I need to do state assignment. Okay, I need to do some state assignment here. Okay, so in this state, in this circuit, in this circuit, in this circuit, how many states I have? Well, let's count them. 1, 2, 3, 4. I have 4 states. Okay, well, how many flip-flops I need? Well, for 4 states, you need 2 flip-flops. Okay, and we're going to assume them that they are Q1 and Q0. Now what I need to do is to do a state assignment, meaning it was helpful for me that I refer to state A, B, C in the initial analysis. But to continue my analysis, I need to map those or assign them binary values based on the values of Q1 and Q0. So I'm assuming I have 2 flip-flops. So let's assume when Q1, Q0, 0, 0, I'm in state A. When Q1, Q0, 0, 1, I'm in state B. And when Q1 and when state is C, I am 1, 0. And when state D, I am 1, 1. So now we go back to these states and we say, okay, what we will do, we will now scratch those. A, we will write 0, 0. And scratch B here and we'll write 0, 1. Scratch C here and we'll write 1, 0. And scratch D here and we'll write 1, 1. Remember, I'm using these state assignment that I'm assuming now to continue solving my problem. Okay, let's recap here. First, I realized that I need from my state diagram 4 states. 4 states meaning I need 2 flip-flops. I assume these 2 flip-flops are Q1 and Q0. So I have Q1 and Q0 can have combinations 0, 0, 1, 0, 1, 1, 0, 1, 1. Now I will assume that A is 0, 0, B is 0, 1, C is 1, 0, and D is 1, 1. And then I go back to my state diagram and write those numbers. Now what I'm doing here, or at this point, I am ready to write or draw my state table. Okay, so let's do my state table in the next slide. Okay, so Okay, so here what we will do is um, okay, so here's what I did is I have the state machine right on the left here, and what I would like to do right here is now construct the state table. Okay, so let's do that. So we need to construct the state table. So I'm gonna use okay, let's see, um, yellow color here. So I'm gonna have a state table. So I have here one for present state. Okay, and one for, so this is present state. Okay, for Q1 and Q0, and then an input which is X. Okay, so these are my inputs to the circuit. Now then what, then next state, which is for Q1 and Q0. Okay, and then my output, which is Z. Okay, so now we'll have this construct this table. Okay, so here's I have two here, half it, and the other half of this guy, half, and the other half of this guy, and I have this guy, and another half for this guy. Notice I left this part on the right hand side empty purposely. I'm going to use this very shortly. Okay, so let's see. So here Q1, Q0, X, Q1 next state, Q0 next state, and output Z. Okay, notice now I'm gonna read the uh, the uh, uh, the state diagram. Now, what I did before, I said in terms of state assignment that this will be for me 0 0 0 1 1 0 1 1. All right, so if I am in state A, which is 0 0, right, depends on x. If x is 1 or if x is 0. If x is 0, I am going to stay in my same state, 0 0. But if x is 1, I'm going to state B, which is 0 1. Okay, now let's go to state B, 0 1. Okay, depends on the input here, 0 1. If I receive an input of a 0, I go to state C. If I input of a 0, I go to state C. If I receive an input of a 1, I stay in same state, which is B, which is right here. Okay, all right. Now I am in state C, which is 1 0. All right, it depends on the input. Right, in state C, if I receive a 0, I go to D, which is 1 1. Okay, if I receive a 0, so here I'm sorry, a 1, so I go to a state B, which is 0 1. Final state 1 1, which is D, depends on the input. Okay, so notice, of course, now here in my table, as we said before, these are my input cases in the state table, the present state and the input X. If I am in state D and I receive a 0, I go to state A, which is 0 0. If I am in state D, which is 1 1, and I receive a 1, I go to state B, which is 0 1. Okay, all right. Now for Z, we have zeros all over until I find my pattern, which is when I am in state D and I received this one, and then I go to with an output of a 1. Now the question here, um, what do I need to do next? What we need to do next is we need to compute. Remember, I need to design flip-flops and I need to understand the input equation of the flip-flops. Now I have two flip-flops. And my design, I'm going to assume I will use JK flip-flops. So for every for Q1, I'm going to have input J1 and K1. They are inputs for Q1. And then for Q0, I'm going to have J0 and K0 for Q0. Okay, so these are the inputs, J1 and K1, inputs for Q1, and J0 and K0 inputs for. Now I need to find their values. Well, how do I find their values? Well, we need to use something called the excitation table. And the excitation table it says what? If you have the present state, which what I have now, and the next state, I will provide for you the inputs. And the excitation table for the JK flip-flop is the following. If you have the present state, QT, okay, and if you have the next state, QT plus 1, okay, then JK values are the following. So 0, 0, 0, 1, 1, 0, 1, 1. Now, if my present state is 0, let's use a different pen here. If my present state is 0, okay, and next state is 0, we call this state, we are kind of, we have no change. I can achieve this either by saying 0, 1, or 0, 0. So that's why K is I don't care. So I can achieve this transition here from here to here by J being 0 and K 0, or J 0 and K 1. So we said, you know what? So UK is a don't care, right? Because you can be a 0 or a 1. Now, if I change from 1 to 1, again, there is no change. And here I can achieve this by 1 0, 1 on the J and 0 on the K, or 0 0. So I say I don't care on the J and a 0 on the K. Now, what happens if I change from 0 to 1? Well, 0 to 1, I can achieve this by either 1 0 or 1 1. So I said, okay, well, this is really a 1 don't care. Because notice I'm setting the flip flop, so I can achieve this by 1 0 or 1 1. Okay, okay. So how about 1 from 1 to 0? I can achieve this by 0 1 or 1 1. So I don't care and a 1. Okay. Now I go back to my table here and I start reading these values for the present state and the next state. So let's start with Q1. I have a present state of a 0 and a next state of a 0. So I go back to the table. 0 0 meaning that the JK is what? The JK should be 0x. So 0 0, the JK should be 0x. Okay. Now let's look at the next pattern. The Q1 is a 0 and the Q1 is a 0. Same thing. JK should be 0x. Now, let's look at the next pattern. Let's use a different color here, for instance. When Q is 0 and Q1 present state is 0 and Q1 next state is 0 1. So I come, so 0 1. So the table says from 0 1 is 1x. 1 on the J and X on the K. Okay. Now, how about the next present state 0 0 2, next state 0 0, and this is 0x. Okay. And how about if I do from present state 1 to next state of a 1? So 1 to 1 is x 0. Okay. Now, how about if the present state is 1 on Q1 and the next state is 0? So 1, 0 is from x1, x1. And you will see the other patterns are the similar, so we'll fill with the same values. Now let's take a look at Q1. Now when Q1, let's use a different color here. Q1 here, when the present state is 0, right, and the next state is 0, so this is 0x. When the present state is 0 and the next state is 1, so this is what? 0, 1, 1x. Okay, when the for Q0, when the present state is 1 and the next state is 0, so 1, 0, 1, 0. So this is the pattern. So I need this x1, x and 1. And present state for Q0 is 1 and next state is 1. So 1, 1, x 0. Okay, and present state is 0. Next state is 1, 0, 1, 0, 1, 1x. Okay, and a similar one to the next one. And present state of 1 and next state of a 0, 1, 0, 1, 0. So that will be 1, 0, x1, x and 1. Okay, and present state of a 1 and the next state of a 1, so this will be x0. Now next what I now obviously here I can see that now I have my inputs. So see, you can see that here I have here my inputs to the flip-flops, and I draw this these columns to differentiate between the j and the k of different flip-flops. Okay, their values. Next, what I do, I use k-maps. K-maps for what? K-maps to do minimization. So obviously I need to draw the equation for j1 equal da 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 and k1 equals da 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 and j0 equals da 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 and k0 equals da 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 da. So to do that I need k-map. Okay, so let's do k-map here. So I need to say use a eraser here a little bit. I need to, okay, so let's use a K-map here. Oops. Okay, so let's use a K-map for J1. I need to calculate J1. So let's draw the K-map here for J1. Obviously this is Q2, Q1, Q0, X. So 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now, I need to read this column, which is the J1 column right here, right here. Okay, and I need to put the numbers in the table. So I have here what? I have here 0, 0, right? Let's do this with this different color. Say for example, I have here 0, 0, 1, 0, okay, and x, 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 x. Okay, so J1 equals what now? Well, it turns out I can do a minimization right here. I can do a minimization right here. So this is, I can combine this for minimization, and that gives me what? Q0 x prime. Q0 x prime. This is for J1. Let's do now the case for K1. Let's do for K1. Okay, so for K1 again we draw the map. Okay, so here is the map, a K map. Again, my inputs are Q1, Q0, and X. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Okay, so now let's get the value of K1, which is right here. This is K1. x, 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 and then I have 0, 1, 1, 1, 1, 0, 1, 1, 1. Okay, so let's do minimization here. Okay, so we can do the minimization. So here is 1 and here is 1. So this becomes what? This becomes K1 equals Q0, Q0 or X. Okay, all right. Now, so let's continue with the K-map. What else I need? I need a K-map for J0. So let's do J0 now. Q1, Q0, X. So this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So let's do J0. Here is J0 right here. Okay, let's plug the numbers. Okay, so let's get this color here. And then, so 0, 1, XX, 0, 1, X, X, and then I have 1, 1, X, X, 1, 1, X, X. So this is what I could do here is I can have I can have these guys together. Let's get a red color here. I can have these guys together, all of these and all of this. So J0 equals what? J0 equals Q1 plus X. Okay. Final K-map for what? For K0. Okay, so let's draw the K-map. Okay. Again, Q1, Q0, X, right? And let's have this here. So okay, so this will be X, X, or X, X, 1, 0, X, X, 1, 0, X, X, 1, 0. Okay, and in this case, what I could do is if I can take these together, all right, that will be X prime. So now notice I build the K maps for what? I build the K maps for all these inputs for to minimize J1, K1, and J0, K0. We still have to have the equation for Z, but Z obviously is only one in one place when Q1, Q0, and X are all ones. Okay, so now what do we need to do? The final step that we need to do is to draw the circuit. Okay, now I have all these components are ready for me. So what I need to do, see if I can slide this to, I need to draw the circuit. Okay, so my circuit consists of what? Let's draw the circuit. So I have two flip-flops. I have Q1. Okay, this is Q1. This is the first flip-flop, and I have Q0. Okay, so Q0. Okay, so this is Q0. Now the inputs to the very first flip-flop is J1 and K1. And the input to the second flip-flop is J0 and K0. Okay? Now, I have computed J1 and K. So from my previous computation, from the equations, you can see that here, J1 and K1, I have already counted them. So J1, for example, QX prime. Okay, J1 is QX prime. Q0, so this is, and K1 is X or Q0. This is K1. Don't forget the clock for a flip-flop. So this is a clock, say CLK, CLK. I messed this thing up. So so this is CLK, and this one is also has a CLK. So now what's the J0? We said J0 has X and Q1. X, we found out that it is X or Q1, and Q0 is what? It is X prime. Okay, so here are the two flip-flops, their inputs. I am left of the output, which is what? Which is ANDing of a Q1, Q0, and X, and this is Z. Okay, that's it. This is the full this is now my full circuit, and this is the complete design of the circuit, from state diagram to state table to the input of the flip-flops to the minimization of the flip-flops, and then finally to drawing the circuit. Now notice what I did here. I used what? I used JK flip-flops, JK flip-flops, and their inputs is J1 and K1. I could have used what? I could have used D flip-flop. Okay, so what if I use D flip-flop? It's the same thing. It's the same kind of solution, but where we differ is in the input of the flip-flops, So here, notice that the flip-flops, their inputs is what? D0 and D1, D0 and D1. And notice that here, D0 and D1. Why D0 and D1? Well, because if we are using D flip-flops, okay, so instead of JK, we'll have an input D and Q. So this is Q1. It has an input of D1, and Q 0, and it has an input of D0. So here's a clock. We don't forget it, and here's the clock as well. We don't forget it. Okay. Now, so um, we need to compute from the present state and the next state the values of the inputs, right? Well, it turned out the values of the inputs are much, much easier in the D flip-flop than the JK. In fact, nobody uses JK. In fact, nobody uses T flip-flops. Everybody uses D flip-flops. And for this very simple reason that I'm going to tell you. The input of the flip-flops equal the next state. In fact, look at this column. 0, 0, 0, 0, 0, 0 for D1Q1. 1 0 1 0, the same. You just copy the column, and in the exam, if you are short on time, don't even create columns for D1 and D0. Assume D1 equals Q1 next state, and assume D0 equal Q0 next state. So these columns are identical, they are the same, and so are those two columns. They are identical, Q0, and that's why everybody loves loves excuse me, uh, everybody loves the D flip-flop, because the input value equals next state. We have one input, we don't have two inputs like JK, and the input file. So in fact, the excitation table, excuse me, the excitation table is very simple. Input values equals next state. So now, if I construct, so I need to construct two see, if I need to construct two K maps. Whoops, sorry. One for D0 and one for D1. Now, D0 equals this. Okay, 0, 1, 0, 1, and 1, 1, 0, 1. Okay, if you do the minimization, okay, so you minimize those and those. Okay, here is Q1, Q0X. Okay, so that ends up being X or Q1, Q0 prime. Okay, and for D1, okay, so for D1 it is 0 0 0. I'm sorry, D1 0 0 0 1. Okay, wait a minute. Uh, 0 0. Oops. It's just take. Okay, so for D1, 0 0 1 0 and 1 0 0 0. Okay, so this is equals to Q1 Q0 prime X or Q1 prime Q0 X prime. Okay, now I can draw their circuits. Okay, so this one here is an OR gate of what for D1? An OR gate of let's see, I have so I have Q1 Q0 prime X. Actually, this is probably X prime, right? Q1 prime 0. Okay. Yes. Okay, so Q1 prime Q1 Q0 prime. Let's see if I can do this a little cleaner. So this is Q1 Q1 Q0 prime and X, and this one Q1 prime Q0 and X prime. Okay, and then this D0 is another OR gate of I have here X and I have here Q1 and Q0 prime. Okay, and the Z does not change. Okay, the output Z, you have Q1 Q0 and X. So this is the same circuit using what type of flip-flops? D flip-flops. Okay. Okay, so just one last comment here. In your slides, you will see that the excitation tables, the various excitation tables for flip-flops. So let's just um, take it here. Um, the various excitation table. Here are the various excitation table for so we have used this, the JK. We have used the D flip-flop. Notice my observation. The D input equals what? The next state. Okay, so the excitation table, what's the job of an excitation table? It maps the output of Q and Qt plus 1, the present state and next state, to the input. It tells me what is the value of the input. What is the value of the input? What is the value of the input for the different flip-flops? We use this and we use this, and then the T flip-flops. One thing about T flip-flop, if Q and Qt plus 1 are equal, then the T flip-flop is 0. If they are different, then it is 1. Okay, so you can use the appropriate excitation table for the appropriate flip-flop, the one that you are given in the problem in the assignment or the exam. With that, we complete the discussion of designing a sequential circuit from the description all the way down to the circuit with the specified flip-flop type. One final note, and I'm going to repeat this: the most widely used flip-flops are the D flip-flops. Thank you very much.